Hey folks, good morning. I'm Simon. Thanks for having me. I'm here to talk about using Codemods to refactor your JavaScript using JavaScript. So real quick, here's some background on me. As Jess said, I'm a software engineer at Attune based out of New York City. By using data, design, and technology, Attune makes insurance as easy as it should be. P.S. We're hiring. Come talk to me after if you're interested. I'm also an instructor at General Assembly in New York. I've taught part-time evening courses in front-end web development, JavaScript, Python, as well as many short workshops. I'm sure some of you folks are maybe a bit tired right now. That's totally cool. Maybe you're waiting for your coffee to kick in. Hopefully you're not full on asleep. I don't think anybody's asleep. I'm looking at the audience, so that's good. And I'll try to keep it that way. Stay awake, and I promise to make it worth your while. So let's get started. I'm sure some of you are also thinking, code what? So what exactly is a code mod? Code mods are scripts used to help with refactoring code. The term originated from a tool named Codemod that was open source by Facebook. This first tool used regular expressions and Python for the actual refactoring scripts. Facebook also open sourced JS CodeShift, the tool we're going to see in today's talk. Essentially, we can programmatically refactor the JavaScript files in our codebase by writing transformers in JavaScript. I know, mind blown, right? There's an Inception joke in here somewhere. I just couldn't think of it, but it's cool. And that sounded pretty wild, right? Actually, if we really think about it, code mods are pretty mainstream. If you've ever had to upgrade React, maybe you saw this blog post back in the day, there's a good chance you would have seen code mods mentioned in the React blog and the documentation and all that good stuff. So this is a personal opinion alert, but I think mainstream technologies are great. There's a lot of risk with using bleeding edge or not fully baked libraries, especially with production code bases. When writing code at work, I'd much rather use a mainstream library. Okay, now that we're done with my personal opinions, what would it actually look like if we ran the code mod mentioned in that blog post? So let's take a look at it in action. We're running the class transform code mod on a React application. The goal is to transform the create class components into ES6 classes. Notice how we're processing 500-ish files. We did them around 50 at a time. We had 3 workers, all that good stuff. So let's take a look at that command that I just ran. JS CodeShift is an NPM package. It's installed globally, all that good stuff. We're going to see JS CodeShift a lot in this talk. It's a tool that we'll use to actually run the code mods. Here's a quick before and after of that React component, or what an exampled React component might look like. Notice how the React create class was changed into an ES6 class. This is what the code mod allowed us to do without modifying the files ourselves to make that change. There are a few other changes that you might notice in here as well, such as the property initializers. So I'm sure some of you folks are still not convinced yet that code mods are worth the hassle. You know, we could have modified that file ourselves. It would have taken us a few minutes, so why bother with them? You might be thinking, hey, I have regular expressions, right? I know how to use them. So you can make complex find and replace changes with even more complex regular expressions, but code mods allow us to make changes that are actually impossible with the regular expressions. JavaScript, the language itself, is a first-class citizen when writing code mods. On the other hand, with the regular expressions, they only really understand the text content of a piece of code. Furthermore, code mods actually unblock application-wide refactors by making them easier to perform. These changes might be required because a library like React, as we saw previously, has updated its API. We could also have updates on an internal API in our codebase. You might want to adopt a new pattern or a new standard. These are changes we would have to make manually if we didn't use code mods. Also, the JavaScript ecosystem as a whole tends to evolve at a lightning pace to language and library updates. Your codebase will have to evolve over time as well. In a very old codebase, you might have files that have been touched in years. So that usually results in tech debt, but code mods help us reduce tech debt by allowing us to perform programmatic refactors to modernize our code bases. Lastly, code mods, when used properly, will actually save significant amounts of developer hours when refactoring an application. At a previous company, at a previous role, we actually saved hundreds of developer hours by using Codemods to modernize thousands of JavaScript files in a single application. And honestly, that was great and all, but Codemods are also just really fun to use as well, so that's the highlight there. So you might be wondering, what are some possible refactors that we can perform? Let's walk through some of these refactors. This is just a sample of them. There's a lot more that you can do. You can use Codemods to refactor older ES5 syntax into ES 2015+. There are a bunch of transformations out there. There's quite a few open source ones on GitHub. There's an example here. There are ones for changing from require to import statements, transforming function expressions into arrow functions. We're actually going to look at that code mod later on today. And there's so much more. As we saw previously, there are code mods to make upgrading React itself easier. You can use them to refactor your components to unblock upgrades as React's API changes and evolves over time. And if you currently have prop types, you can actually use a code mod to convert them into TypeScript types. That's super exciting, and it should make adopting TypeScript much, much easier. All right, so hopefully by now all of you folks are convinced that code mods are worthwhile. I don't see anybody sleeping just yet, so that's great. So let's review how code mods using JS CodeShift actually work internally. And then we'll introduce concepts we'll need to implement our own code mods. So here's a GitHub repo for JS CodeShift. It was open source by Facebook. We'll use JS CodeShift to run the code mod scripts on our JavaScript files. Here's the official description from their README. Let's try to parse that official description. And I'm also really glad that that build is passing. So the first part is the easy part, right? JS CodeShift will run our transformation scripts against the files we want to refactor. It'll provide a nice summary in the end. That's all great. We saw this before. Let's actually break this down. Here's an example of using JS CodeShift along with the summary of the output. Notice how we're passing in that transform file, class.js, from the React code mods. The actual input is the to-do folder in our current directory. And JS CodeShift has a bunch of handy options for adjusting the number of CPUs, performing dry runs without making any changes, and ignoring files. We can also provide our own options, as we have here. So we saw the first part. That was fun. The second part is also fun, but a little bit more difficult. So JS CodeShift uses the Recast package internally. It has whatever methods Recast has, but provides a more convenient API for those methods. So what's Recast? Here's a GitHub repo for Recast. Recast is a package we can use to parse a piece of JavaScript code, manipulate that code, that is actually transform it, and then finally return it back out. It's great because if we use Recast properly, it'll maintain the same style as the original code before any of our automated refactoring. Let's focus in on that parsing step. What does that mean for us? Recast supports different parsers like TypeScript, Flow, and Babylon. That's the parser behind Babel. That means that JS CodeShift itself supports those parsers. That does raise a question. What exactly happens when Recast parses our JavaScript? Recast generates an abstract syntax tree, or AST for short, from our JavaScript. So please don't worry if that's how you feel right now. Let's actually take a look at abstract syntax trees real quick. It's a pretty heavy topic for 9:30-ish in the morning, but I think we'll get through it. An abstract syntax tree is a data structure which represents a piece of code. It includes all the relevant language constructs, and we'll see some of those constructs later on. Abstract syntax trees are widely used in compilers. If you use a tool like Webpack or ESLint or Babel, those tools make heavy use of abstract syntax trees. So it's not quite like that tree right there. There's a Cascadia joke in there somewhere, but let's actually talk through the tree aspect. So trees are data structures that consist of nodes that are linked to one another. So here is an example of a tree. At the very top, we have node 1, that is our root node. We'll see this concept of a root node later on as well. So we can see that node 1 is the parent of nodes 2 and 3. And also notice how node 2 has 2 child nodes as well. If you're not super familiar with tree data structures and their associated algorithms, I highly encourage you to get into them some more. They're pretty neat. So going back to abstract syntax trees, the nodes in an abstract syntax tree directly describe the structure of our programs. So let's take a look at a single node. Here's an example AST for the string hello world. With JS CodeShift, the nodes are plain JavaScript objects. There's no magic going on here. We can identify nodes by their type. So, spoiler alert, that one is the type literal, and the values correspond to our string hello world. For a more complex example, let's take a look at this function declaration up there. So you can see the type is function declaration, not too bad. And we even have access to its name and so much more. We can see the name property and all that good stuff. This is just a JavaScript object that we can interact with. What's great is that we can use this tool, AST Explorer, to actually inspect the abstract syntax tree for a piece of code. We just plop it in there and see the tree itself. We need to manipulate the abstract syntax tree for a file in our Codemods. So this tool is extremely helpful for figuring out the structure of our current code along with what types we want to change in the end. So we can even go further. The Recast package uses the AST types package, which actually wraps these abstract syntax tree nodes in these path objects. So these path objects are fantastic because they allow us to do tree traversal, iteration, node modification, and so much more with a pretty convenient API. And the AST types package also includes builder methods exposed in JS CodeShift for creating these nodes in the abstract syntax tree. So in the context of that tree from before, let's see what this unlocks for us. So we have our tree from before. Because of the AST types package, we can traverse up from node 4 to node 2. We can also modify nodes. We want to change a piece of code. So let's say we're done with the node 2, we want to make it better, it's not doing it for us. We can change node 2 to node 6. Going even further, we can actually add new nodes. We can add new parts to a program. So here we're going to add a child node to node 3. Now we have node 7 up there. So as we begin to combine these concepts together, we can actually begin to write code mods. So let's dive right in. Here's a general overview of the process. First, we'll need to parse our source code to generate the abstract syntax tree. After that, we'll need to actually modify the abstract syntax tree as required for our refactoring goals. That means that we'll need to traverse the tree for the nodes we care about, access them, and then update those nodes as well. And finally, using our abstract syntax tree, we can regenerate our source code. The files have been modified, and we're good to go. The refactoring is done. We'll perform the process in a transformation file. This is a lot like that class.js file we saw from before. It's just like any other JavaScript file. We'll pass the transformation file as a flag to JS CodeShift. So the transformation file is simply a JavaScript module. It exports a function that returns our modified source code. We'll have to do the same 3 steps from before. We'll have to parse our source code in this file. We're going to update the source code as required. And then we'll return our updated source code. So let's take it step by step and do each step. So looking at the parameters of this function, we have 3 up there. The first parameter file actually gives us access to the file we're changing. It gives us the file's path and the source, all that good stuff. This is the file that we're changing programmatically, or we're refactoring programmatically. The second argument has aliases to JS CodeShift itself. So it allows us to collect statistics, generate reports, all that good stuff. And the last argument is an object that contains all the options that were passed to the JS CodeShift command. So this includes any user-defined ones, so our code mods can be extremely flexible depending on the changes that we want to make. So let's take a look at the basic setup for our function. Usually folks like to alias references to JS CodeShift as J. It's a very convenient variable, a lot easier to type out. For the first part, we'll use JS CodeShift aliased as J to parse the source code of the provided file. JS CodeShift will handle passing in one file after another, so we don't have to worry about any of that. Here, we'll return the root node of our abstract syntax tree. So usually folks have these methods all chained together, but I separate them out to make it easier to read. After that, we'll need to actually modify the AST itself. That one's a little bit more involved. Let's hold off on that for a second. In the end, we can regenerate our source code. from the abstract syntax tree by calling the toSource method. Here's where things get interesting. We're returning a value at the very bottom, and that's just a string. If we return a string and it's different from the original source code, that means the transform was successful. Go us, you did that part successfully. If we return a string, but it's the same as the original source, we might have made a mistake. The transformation was unsuccessful. And at the very end, if nothing is returned at all, that's okay. That just means that the file wasn't supposed to be transformed. We can skip that file. So we saw that root node from before. Let's talk about that real quick. So this root node variable is an example of a collection in JS CodeShift. These collections in JS CodeShift, they consist of Recast's path objects. So all the path objects we have from Recast, we just group them together, and then we have this collection in JS CodeShift. And those path objects, those are the actual nodes in our abstract syntax tree. So those collections are pretty great because JS CodeShift exposes methods for finding, traversing, and updating the nodes in our abstract syntax tree. The API is extremely convenient, and we're going to see it in a second. It's convenient because these methods themselves, they tend to return collections. So back in the day, when we all used jQuery, it's a lot like that. With jQuery, we'd have a collection of DOM nodes that were returned, and we'd modify them. It's the same principle here. JS CodeShift actually implements a fluent interface and relies heavily on method chaining. We have this collection, and we start calling up methods upon methods on that collection. When we're done, we just return the source. So you can actually write these transformations in the AST Explorer tool itself. It's pretty convenient. If you're writing your own code mod, I highly recommend starting here. All you have to do is specify the transform option and choose JS CodeShift as the value, as I have up there. So looking at this, we have the transformation file on the left and the output on the right. This transformation is a bit silly. All it does is reverse the characters in the function's name. So maybe not the best code mod out there, but we're going to take a look at a good one in a second. So let's take a look at the modifying step. So here's a more realistic example. We're going to write a code mod together to transform function expressions into arrow functions. So arrow functions are pretty hip, so we're going to go with those. Looking at this, the first step in actually writing a code mod is determining which cases we want to support in our transformation. We don't have to handle every single case. And there are plenty of cases that we just can't handle. So using these three functions as examples, let's talk through our thought process. At the very top, we have function one. Function one is honestly pretty benign. So it's like any other function expression. It returns the sum of two parameters, num1 and num2. We should be able to transform this into an arrow function pretty easily. And we can actually make it into a very fancy arrow function. There are no curly braces, it looks super clean, so we have to be able to handle that in our transformation script. For function 2, this one's a little bit more involved, right? It has our num1 and num2 parameters, but we're also handling the case of having a variable declaration inside of our function body. And we can have other statements inside that as well. We want to make sure that if there are any variable declarations, if there's any other work happening in our function body, that we support them properly. So we're building out these test cases. It's almost like writing a unit test for a piece of code. So in function 2, we have our num3 variable. It's not doing much for us. All it's setting is the value to 0. But we want to make sure that that is still preserved after our transformation. All right, last one, we have function 3. And this one, we actually can't transform programmatically. So if we take a look at it, we're using the this keyword inside of the body of that function. This is where things get a little bit hairy. The this keyword is handled differently in arrow functions. And we want to make sure that we don't change any of the actual functionality of this piece of code. So we don't want to automatically transform this function. We want to avoid changing functions like function 3. We want to make sure the actual logic in the transform function is the same as the original function. So we're going to have to write some code ourselves to avoid cases like this, where we're using the this keyword. Let's take a look at our transform script, focusing on the code for modifying the abstract syntax tree. First thing we'll do is grab all the function expressions. So we have this find method. It's exposed by JS CodeShift. And we can use the AST Explorer tool from before to figure out the actual identifier we care about. So we're going to find all the matching nodes that are function expressions, and we'll access them through this fn expressions variable. This is a collection of path objects, And once we have that collection, we can start to write logic against it. So here, we're avoiding all the function expressions that have the this keyword. We don't want to break any of our code from before. So we're going to filter them out, and that filter method is also exposed by JS code shift, so we're good to go. We're going through every single function expression and just removing the ones that have the this keyword inside the function body. So we want to avoid transforming those functions. Size and other methods are just exposed by JS code shift. And this last portion is a little bit hairy, so let's talk through it. So FN expressions know this. That one is all of our function expressions that don't have the this keyword. And what we're going to do is we're going to use the replace with method to actually change the function expressions that we care about. We're going to go through them one by one and just change the ones we care about. We're going to grab the body's content. We're going to grab all the parameters we need, all that good stuff. We're also going to check if we can transform these into one-liner arrow functions with that logic there. And all these values are in the AST Explorer tool. We don't have to memorize them. No one is born knowing these values. We can always just look them up. And we can figure out what we care about. Once we've verified that that one-liner is safe, we're good to go, and we can make that change. So taking a look at this, we're returning that arrow function expression from our callback. And at the very end, once all of our work is done, we can return the original source code. So in the end, we get back this nice string, and JS code shift handles updating our original files, and we're good to go. We transform those function expressions into arrow functions for those specific cases. So we just saw an example of how to write a code mod. But let's talk through some tips for working with code mods in your actual production code bases. So we worked through those 3 function expressions in one file as an example, but most of our code bases include hundreds or thousands of files. So let's talk through some tips. I learned most of these the hard way, so you folks can benefit from my past frustrations and mistakes. First thing I would highly recommend having safety nets in place before even attempting to use code mods. Make sure you have extensive unit and integration tests. I would also say don't treat pull requests with code mods applied as any different than a regular change. So you should still do things like code review and all that good stuff. Don't treat code mod changes any different than regular human changes. What I also recommend is when merging in code mod modified files, don't make any other changes in that branch. So don't rename something, don't adjust white space, do not do anything else. Modifying the code manually actually makes it very hard to undo and redo those transformations. If you absolutely need to make those manual changes, you should be very explicit in the pull requests. Otherwise, I would just let the code mod do the work for you. And if possible, split up these large code mod refactors into multiple smaller pull requests and deploy them individually. This makes it very easy to diagnose a bug. This way you can roll back easily if needed. And as you go along, try to write internal documentation for a code mod, because eventually somebody will get blamed that refactored code. And if they see a pull request, an empty pull request description for a 1,000-line change, that's not a good thing. So I highly recommend linking to your internal documentation in your pull request as well. If somebody has to revert your transformer code, they should have enough information to reapply that transformation later on. And honestly, I would say treat every code mod you've written internally as actual code. You want them in a separate repository, you want documentation, you want to version them as well. And the last part, your code mods don't have to handle every single case. So you can modify any files that are very tricky manually and just skip them in your pull request. We saw with a lot of the open source code mods, they don't actually handle every single case. So there's definitely a time trade-off. So if you see yourself spending too much time writing a code mod, just skip it and do those changes manually. With all that said, thank you folks so much. I hope all of you have fun using code mods next week at work, maybe later today. Feel free to come find me afterwards if you have any questions. Thank you folks so much.